Today we are going to learn about handling missing data with Scikit-learn Imputers. We will explore various imputation techniques and decide on the best strategies for maintaining data integrity and improving model performance.
Welcome to our educational video on handling missing data with Scikit-learn Imputers. In this video, we will delve into various imputation techniques provided by Scikit-learn. Handling missing data is a critical step in data preprocessing, as it ensures data integrity and improves the performance of predictive models. Over the next 15 minutes, we'll explore different imputation strategies, from simple to more complex techniques, and provide practical coding examples. By the end of this video, you will be equipped with the skills to effectively manage missing data in your datasets. Missing data can significantly impact the quality and reliability of your datasets. When data is missing, it can introduce bias, reduce the accuracy of your models, and impair data integrity. There are three primary types of missing data: missing completely at random, MCAR, missing at random, MAR, and missing not at random, MNAR. MCAR occurs when the missingness is entirely random and unconnected to observed or unobserved data. MAR happens when the missingness is related to observed data but not to the missing data itself. MNAR arises when the missingness is related to the missing data itself. Understanding these types is crucial for deciding on an appropriate imputation strategy. Imputation, or filling in missing data, is vital to ensure that your analyses and model predictions remain accurate and unbiased.
SimpleImputer is a basic yet powerful imputation tool in Scikit-learn that offers several strategies for handling missing data, including mean, median, and most frequent imputation. The mean imputation technique replaces missing values with the mean of the available data, which is useful when data is symmetrically distributed. Median imputation is preferred when dealing with skewed data, as it replaces missing values with the median, reducing the effect of outliers. The most frequent imputation fills in missing values with the most common value in the dataset, which is particularly effective for categorical data. Each of these methods has its specific use cases, and choosing the right one depends on the nature and distribution of your data.
IterativeImputer is a sophisticated method available in Scikit-learn for handling missing data through multivariate imputation. Unlike simple imputation techniques, IterativeImputer models each feature with missing values as a function of other features, iteratively updating the imputed values. This iterative process continues until the imputed values converge, ensuring a more accurate estimation of missing data. IterativeImputer is particularly advantageous when dealing with datasets where multiple variables are missing at the same time or when the relationships between features are complex. It provides more robust and stable imputations compared to simple methods, making it suitable for datasets where preserving the underlying data structure is crucial.
Imputer is another innovative imputation technique provided by Scikit-learn, leveraging the k-nearest neighbors algorithm. This approach fills in missing values by finding the k-nearest neighbors of the missing data point and imputing the missing value based on the average or median of these neighbors. Imputer is especially effective when the dataset exhibits a natural clustering or when similar instances can be identified. This method is beneficial in scenarios where preserving the local structure of the data is essential, and it can adapt to both numerical and categorical data. The choice of k, or the number of neighbors, is a critical parameter that can be tuned based on the dataset's characteristics. In this section, we'll dive into practical coding examples using SimpleImputer and Scikit-learn. We'll implement mean, median, and most frequent imputation techniques step by step. First, ensure you have Scikit-learn installed in your Python environment. Start by importing the SimpleImputer class from Scikit-learn.impute. For mean imputation, initialize the SimpleImputer with the strategy parameter set to mean. For median imputation, change the strategy to median, and for most frequent, set it to most_frequent. Next, fit the SimpleImputer object to your dataset using the fit_transform method. This method will automatically handle both numerical and categorical data, making SimpleImputer a versatile tool for different types of datasets. Let's explore how to implement the IterativeImputer using Python. Begin by importing IterativeImputer from Scikit-learn.experimental. The experimental module indicates that IterativeImputer is still in development, but it's powerful for multivariate imputation. Initialize an IterativeImputer object, which can be customized with parameters such as max_iter and initial_strategy. The max_iter parameter specifies the number of iterations for the imputation process. Fit the IterativeImputer object using the fit_transform method on your dataset. This method will iteratively fill in missing values, taking into account the relationships between different features, making it suitable for complex datasets with interdependent variables. To implement an imputer in Python, start by importing the Imputer class from Scikit-learn.impute. Initialize an Imputer object, specifying the n_neighbors parameter, which determines the number of neighbors to consider for imputation. The choice of k, or n_neighbors, can significantly affect the imputation accuracy, so it's essential to experiment with different values to find the best fit for your data. Use the fit_transform method to apply the imputer to your dataset. This method efficiently handles both numerical and categorical data, making it a versatile option for various datasets. Imputer is particularly useful when you expect the missing values to have a similar distribution as their neighbors. Choosing the right imputation strategy is crucial for ensuring the integrity and effectiveness of your data analysis. Consider factors such as the size and distribution of your dataset, the nature of missingness, and the data types involved. For numerical data with normal distribution, mean or median imputation might be sufficient. In contrast, for categorical data, the most frequent strategy or an imputer could be more appropriate. Evaluate the imputation methods by comparing their impact on model performance and checking for biases introduced by the imputation process. Ultimately, the chosen strategy should align with your analysis goals and the specific characteristics of your dataset.
Categorical data presents unique challenges when it comes to imputation, as it doesn't have a natural numerical order. SimpleImputer can be used for categorical data by setting the strategy to most _frequent, which fills in missing values with the most common category. An imputer is another effective approach, as it identifies the nearest neighbors based on other features and imputes the missing category accordingly. When handling categorical data, it's essential to consider the relationships between categories and other features in the dataset. Always validate the imputed values to ensure they make sense in the context of your data and do not introduce bias. After performing imputation, it's crucial to evaluate its impact on model performance. One effective way to assess this is by comparing the performance of models trained on imputed data versus those trained on original, non-imputed data. Use cross-validation techniques to ensure that the evaluation is robust and not influenced by random sampling. Look for any biases introduced by the imputation process that could affect the model's predictive power. Identifying these biases will help you fine-tune your imputation strategy and make necessary adjustments. Remember, the goal is to optimize the imputation process to enhance, not hinder, your model's performance.
In conclusion, handling missing data is a fundamental aspect of data preprocessing that can significantly influence the outcome of your analyses and models. We explored a range of imputation techniques, from SimpleImputer's basic strategies to more advanced methods like IterativeImputer and Imputer. Remember, the choice of imputation strategy should be guided by the characteristics of your dataset and the goals of your analysis. We encourage you to practice these techniques and experiment with different strategies to find the best fit for your data. By maintaining data integrity through strategic imputation, you'll be well equipped to achieve reliable and accurate results in your data science endeavors.